Hello everyone. Welcome to our talk, LinkDoor, a hidden attack service in the Android Netlink kernel modules. In this talk, we will discuss the Netlink attack service buried deep in the Android ecosystem. First of all, let me introduce ourselves. We all come from Baidu AIoT security team. I'm Chaoma. I focus on the Android and Linux bug hunting and exploit, and have already found more than 100 vulnerabilities in the last 8 months. Invoking Linux kernel, Qualcomm, MediaTek, and so on. Han Yan is more interested in IoT and platform security. He was a Black Hat USA speaker. Tim Shah is our leader. He focuses on the system and the software security solutions, and there was a PackSec and HITB speaker. Next we will first introduce the concept of Netlink. You will learn what the Netlink is in this section. And then we will analyze the attack surface of Netlink. You will understand the underlying principles behind the formation of Netlink vulnerabilities. Next, we will show you 4 typical vulnerabilities scenarios. You will get the vulnerability modeling methodologies in the real world. After that, the POC template and solutions to common vulnerability verification problems will be given. Finally, we will provide vendors with some security suggestions for customizing Netlink. Let's start with the introduction. So what are the local attack surfaces in the Linux kernel? The possible answer may be operations such as our controller, read-writes, device files, system files, process files, and so on. But today we will introduce a commonly overlooked attack surface, Netlink. Netlink is often described as our controller replacement, which mainly used for bidirectional communication between the kernel and the user space processes. Certainly, communication between user space processes is also applicable. Netlink has some features that are different from our controller, such as full-duplex, asynchronous, and multicast, just like the figure below. We divide Netlink into 2 categories according to its usage: classic Netlink and generic Netlink. As shown in the right figure, the generic Netlink protocol ID is 16. It's 16, and the others are classic Netlink IDs. Classic Netlink socket or Netlink socket is supported since 1999 with Linux 2.2. As shown in the following figure, it is a socket family, so its user space programming model uses the Linux socket API. Due to the feature of full-duplex communication, Netlink transfer message has 2 directions, top-down and bottom-up. In the left figure, we can see the Netlink kernel create function will register the input function. The input function is to pass the message received from user space. It receives SKB as the input parameter. The SKB contains the Netlink transfer message. In the right figure, the NL message unicast or NL message multicast function is to send the built-in message to user space. The programming model of classic Netlink seems to be perfect, but why was generic Netlink introduced later? Let's take a look at the classic Netlink kernel registration function, Netlink kernel create. In the right figure. Its second parameter is unit. which represents the Netlink protocol ID. If we want to customize a classic Netlink, we need to add a new protocol ID. In the Linux kernel, the maximum number of protocol IDs is 32. And the kernel has already occupied 22, so the kernel leaves only 10 for customized usage. Of course, we can enlarge the max links, but this doesn't seem a good idea. In addition, classic Netlink is more complex to use because it requires passing the Netlink message by ourselves. The passing macro in the right bottom figure. Therefore, the generic Netlink come into existence. Okay. Generic Netlink socket is supported since 2006 with Linux 2.6.15. All the customized usage can share a single protocol ID 16. When passing the user space messages, we only need to focus on the payload, also known as attributes. In the left finger, we can see that the junior register family function will register the ops and the small ops. The difference between them is that the small ops provides few message handling functions and is simpler. Both ops and the small ops contain the doit function. The doit function is to pass the attributes received from user space. It receives a SKB and an infer as the input parameters. The infer contains the user payload or attributes. In the right finger, for functions is to send the built-in attributes to user space. Okay, after introducing the Netlink's usage, let's analyze that attack surface in depth. First of all, let's take a look at the Netlink architecture. In user space, an application can directly call or indirectly use the libnl to call the Linux socket API to send the Netlink message to the kernel space. After receiving the message, the kernel will route it to the Netlink server system. The subsystem will handle it according to its usage category. Next, we will focus on the message handling mechanism of the Linux subsystem. Classic Netlink transfer messenger may consist of multiple Netlink messages. You can see it in the first line. Each message contains a Netlink message header, user payload, and their pendings. The header size and the payload size should be 4 bytes unlined. The NM messenger header structure consists of 5 fields: message length, content type, additional flag, sequence number, and process port ID. The message length is the total size of a Netlink message. The port ID is usually set to the process ID. The classic Netlink transfer messenger is sent from user space to kernel space by send to or send message function. The SKB will contain the transfer messenger. It is an input parameter of the input function. The input function registered by Netlink kernel create function will pass this transfer message. We can get the transfer message from the SKB's data. The question is, what checks does the Linux kernel Netlink subsystem do on the transfer message? The answer is check nothing. Which means we need to check the Netlink message header by ourselves. It is a dangerous behavior to leave the checking to the developers. How should we securely pass the top-down transfer message, not knowing the attack, not knowing the defenses? We summarize the three possible attack vectors. The first is the developers don't have a correct understanding of the relationship between SKB's length, NIH's message length, and message head length macro. So they don't do any checks at all. The SKB's length is the transform messager's total size. It may consist of multiple Netlink messengers lengths. The NI messenger length is one messenger's total size. The NI message head length macro is one messenger header size. It is a fixed value. A convenient way is that we can do those checks by the NI message OK macro. The second attack vector is developers start parsing the payload structure without checking the payload length. And the third attack vector is developers don't fully check the validity of the payload content. In contrast, how do we attack the building of classic Netlink messenger ascending to user space? All we can think of is combining it with other kernel attack surfaces such as fine operations, socket, and so on. We can reversely deduce the source through the classic Netlink building message, and then we can do vulnerability mining. After analyzing the attack surface of classic Netlink, let's continue to analyze the generic Netlink. The message format of generic Netlink is as shown in the figure below. We can see that the generic Netlink is created based on classic Netlink because their general message format is the same. You can see the first line. The difference is that the payload composition, which contains a generic Netlink message header, a family header, attributes, and their pendings. Each attribute contains a Netlink attribute header, an attribute payload, and their pendings. The family header is optional and customized, so let's focus on the generic Netlink message header and the attribute header. The junior message header structure consists of three fields: commander, version, and reserved. The commander field will instruct the kernel to call which do-it function. The NL attribute structure consists of two fields: Netlink attribute length and type. Together with the attribute payload, they form the TLV structure. The Netlink attribute length is the total size of an attribute, including the size of Netlink attribute header. The Netlink attribute type is the index of attributes array. The generic Netlink transform messenger is also sent from user space to kernel space by send to ascend message function. The info will contain the transfer message. It is an input parameter of the do-it function. The do-it function registered by junior regest family function will pass this transfer message. We can get the transfer message from the infer's attributes field. The same question is, what checks does the Linux kernel Netlink subsystem do on the attributes? The answer is check by NLA policy. The NLA policy, namely Netlink attribute policy, is registered in the junior family structure or junior ops structure. The junior ops policy takes precedence over the junior family's policy. We can see the NLA policy contains an attribute type, length, union, and so on. The attribute type here is the data type of the attribute payload. The length has different means depending on the attribute type. For example, if the type is NLA string, the length is the maximum length of the attribute payload. The union is also used to check the validity based on validation type. All checks on the attributes are done in the validator NLA function. Does the top-down generic Netlink transform messenger parsing have no security issues? Of course not. Let's take a look at some attack vectors due to developer oversight. The first is that the developers neither don't set a policy at all or set an incorrect policy during the policy registration phase. The second attack vector is the developers don't check if the attribute is long during the attributes parsing phase. The third one is developers don't fully check the validity of the attribute payload content during the attributes parsing phase. In contrast, how do we attack the building of generic Netlink messenger send it to user space? Same with classic Netlink, we can combine it with other kernel attack surfaces such as file operations, socket, and so on. We can reversely deduce the source through the generic Netlink building message and then do vulnerability malling. From the preview section, we can conclude that both classic and generic Netlink have some possible security threats. Now let's take a look at some typical Netlink vulnerability scenarios in the real world. Based on the attack surface, we investigated Netlink-related kernel modules from 4 well-known vendors and discovered 38 vulnerabilities and obtained 19 CVEs. All the vulnerabilities have been fixed by vendors. In the left figure, we can see that there are more vulnerabilities related to classic Netlink, and there are also more several. It suggests that we should consider using generic Netlink for customization instead of classic Netlink. In the right figure, we can see that both the upstream and the downstream kernel may have vulnerabilities. But the downstream kernel is more likely to generate Netlink-related vulnerabilities. Let's take a look at the first case. The first case is attacking the parsing of a classic Netlink message. In this scenario, the classic Netlink message is sent to kernel space by send-to function. The kernel will invoke input function to pass in this message. As shown in the right figure, mtk gauge Netlink handler function is registered as the input function by Netlink kernel create function. When receiving a message, it will call mtk battery Netlink handler function for further processing. The mtk battery Netlink handler function gets the Netlink header, namely NIH, from SKB's data field first. Then it gets the user payload, namely date from NIH. The date will be passed into mtk battery daemon handler function. This function will further pass the payload content, namely message. It will memory copy the messager's FGD date field to another variable. The question is, how many security vulnerabilities exist here? Based on the attack vectors, we summarized this case has at least two vulnerabilities. The first one is that it accesses Netlink header without checking the header length. The second one is that it accesses Netlink payload without checking the payload length. Both vulnerabilities will result in out-of-bounds read. For the seeking, all the OOB read data located in the receive buffer? The answer is not necessarily. There are two ways that may result in OOB read outside the receive buffer. The first method is calling setSocket option AP function to set or minimize the receive buffer size. The minimum receive buffer size is typically a few kilobytes. The second method is carefully constructing payloads that precisely fills the receive buffer. This can cause the out-of-bounds read data to be the receive buffer outside, just like shown in the right bottom figure. The second case is attacking the building of a classic Netlink message. The vulnerability mining method is tracing the message sent into user space. As shown in the figure below, we first locate the message sending function message unicast. Then we can describe the entire life cycle of this message. Firstly, an user space process sends a DEK, encrypted DEK request to kernel space by our controller function. After receiving the our controller request, the kernel allocates a requester and sends the requester to user space by a message unicast function. Then it will wait for the processing result. After receiving the request from the kernel space, the user space process will handle it and send the processing result to the kernel through classic Netlink. The kernel will call input function to cancel the wait. Then the requester will be released. Now we understand the entire process flow. Let's take a look at the implementation of the input function. We can see that before canceling the wait, it will find this requester from the global variable gpub crypto controller and copies the processing result to the request. The problem is that the requester isn't protected in any way, which means we may still access this requester even if it has already been deleted and released in another thread. Finally, an use after free vulnerabilities is triggered. This case combines classic Netlink and our controller function. The root cause is unprotected global variable. The third case is attacking the parsing of generic Netlink attributes. KSMBD is a Linux kernel server which implements Symbol 3 protocol in kernel space for sharing files over network. In this scenario, the input is a TCP request. The request will be preceded by KSMBD IPC read function. The KSMBD IPC read function will call general message unicast to send a request to user space, and then it will wait for the response. The user space process receives and handles the request, then it will send the response to the kernel by the generic Netlink. The kernel will call doit function to cancel the wait. Then the memory copy will be performed. Now we understand the entire processing flow. Let's take a look at the implementation of the doIt function. The doIt function is implemented as a handler generic event function. It will pass the attribute payload and the payload size from the info variable, and then call handler response function. The handler response function will copy the attribute payload to the response, and then cancel the wait. Once the wait is cancelled, the KSMBD-IPC read function will return. The response will be passed to the IPC response payloader and its size. However, the size of IPC response payloader doesn't be checked, which may lead to an OOB read occurring in memory copy function. This case combines generic Netlink and TCP. Its root cause is developers don't check the validity of the attribute payload contained. The last case is attacking the building of generic Netlink attributes. Similar to classic Netlink, the vulnerability mining method is tracing the attributes sending to user space, as shown in the figure below. We first locate the attributes sending function junior message unit first. Then we can describe the entire life cycle of those attributes. As shown in the left figure, firstly, a user space process will send a write request to kernel space by write function. Then the receiving function FLP write will be handle the write request and send the result to user space by junior message unicast function, as shown in the right figure. Let's take a look at the request processing function FLP write. The header parameter is copied from the user space. The get date from MCU function doesn't check the validity of length from the header, which may lead to an OOB read to the header during memory copying. This case combines generic Netlink and write function. Its root cause is developers don't check the validity of the writing payload. Okay, now we have understood 4 vulnerability scenarios in the real world. The question is, how do we verify and exploit those vulnerabilities? The first thing is verification. When we want to trigger a risk condition, we often encounter the source port occupation problem. The solution is simple. Neither use the process ID as port in multi-process or try available port to bend in multi-thread. The POC template of classical Netlink is shown on the right figure. We need to fill in a message header and payload by ourselves. For generic Netlink, in order to verify the vulnerability, the first thing is to solve the family ID acquisition problem. Because all the customer generic Netlinkers shares a protocol ID 16. They are distinguished by their family name. We can get the family ID by sending the message on the left finger. We need to fill in a message header, junior message header, and attribute by ourselves. The right finger is the POC template of a generic Netlink. We need to pay attention to 3 functions. Junior send message function is used to build and send generic Netlink message. The junior get family ID function is to get family ID by calling junior send message function. The junior receive message function is used to receive generic Netlink message. How we use here we use an arbitrary reader vulnerability and write word where vulnerability to obtain privilege escalation. The exploitation is very simple. Firstly, we use arbitrary read vulnerability to obtain the address of a credential. Then we can modify the credential by using the write word where vulnerability. Last but not least, how are Netlink-related vulnerabilities mitigated? For the Android system, we can set the target class Netlink socket permission by SE Linux rulers. For the Linux platform, we can check the capnet admin permission by Netlink capable function. Through the above analysis, we can conclude that Netlink is a hidden attack surface buried deep in the Android ecosystem. When customizing classic Netlink, the kernel will do no checks on Netlink messages. When we customize generic Netlink, the kernel will do checks by attribute policy. Generic Netlink does more than classic Netlink, but it also introduces new security reads. We have also prepared some suggestions for vendors. The first one is trying to customization using generic Netlink instead of classic Netlink. The second one is understanding standard Netlink mechanism and APIs before using them. That's all. Thank you for your listening. Any question, please tell me. You can also contact with me on Slack. Thank you very much.